Hello everyone, in this video we're going to be solving Ethernaut's Cashback challenge. Now this challenge is quite difficult and complex and involves a lot of coding, so I'm going to go pretty fast, but I will try to explain everything along the way. And this challenge has to do with EIP7702 and the various mechanics that are involved in it. And before I start reading and analyzing the contract, I just made a quick contract here just to illustrate some of the mechanics of the EIP7702, which are relevant to the problem. So imagine you have a contract A, and here you have an immutable variable, which is this contract. The contract basically refers to itself. And you have two functions, A and B, and you call A first, and inside of A, B gets called in this matter by getting the instance of A and calling .b. And when we do this, we want to look at what happens in the regular case without any EIP7702 delegation, and what happens after a player or an EOA delegates to the contract A. And in particular, we want to know what happens to message.sender and what happens to address of this. And this is very relevant to the problem that we're going to look at. And basically what you need to understand is in the regular case, of course, initially inside of A, when player calls simply A.A or an instance of A, basically inside here message.sender is going to be the player, and address of this is going to be just the address of this instance. And inside of B, message.sender will become the address of the instance because it will be treated like some kind of external call because we're calling it like this. And address of this is going to be unchanged. It's still going to be the address of the contract. Now, when the player delegates to the contract A, things change slightly because now player will no longer call A of A, he will actually call player of A. So he will kind of call the function A on itself. And basically the player, which used to be a regular EOA, now has gained superpowers and can act as a smart contract. And what happens is that now inside of A, inside of this function A, message.sender will still be the player. But what changes is that address of this is also now becomes the player instead of being the address of the contract. So this is a key point. And inside of B, this is another key point. Inside of B, since before the sender was the contract address, but now inside of B, inside of this internal call, the contract becomes the player, so the message.sender will be the player inside of B, which is also very, very key to this problem. And finally, address of this will still be the address of the contract inside of B as it was before. So I just wanted to mention this because this mechanics are going to be very relevant to the problem. So now let's take a look at the problem. And again, for the sake of time, I'm going to assume that you are already familiar with the contract. So I'm not going to go into great detail, and I'm going to assume that you have read it already. And we're told that the system leverages EIP7702 to accrue cashback, and users must delegate to the cashback contract and use the pay with cashback function. And here we're told that our goal is to max out our cashback in every supported currency and walk away with at least 2 super cashback NFTs, one of which must correspond to our address. So here we have a library, which is a currency library, which offers us some methods, mainly transfer, also toID. And this toID is going to be relevant because we're going to be using this toID function in order to get the ID of the tokens. And finally, this is our cashback. This is our main contract. So it has some errors. It has some mappings here. It has the super cashback NFT. And again, I'm going to assume that you're already familiar with some of these properties. But basically, we have the two main levers, which are the pay with cashback function, which is the function that we're supposed to call, and we have the accrue cashback function, which is called internally in the same mechanism here that we just discussed. And so we furthermore see that all of the key things that we need to exploit happen in the accrue cashback. For instance, the cashback is, if we want to max out cashbacks for a currency, this is where it happens. And so our cashback, which is calculated here based on the amount, has to be equal to a maximum cashback, which is calculated like this. And then we are supposed to get the amount of those tokens, so the amounts of the values. And finally, here is where we get our NFT. So if our nonce, which is incremented here using consume nonce, if it's equal to 10,000, then we get the NFT. So this is roughly what the contract looks like. And how we will exploit it, well, first of all, we're going to try and call this function without passing through this function. So we're going to try to call this function directly, and this is possible because the author of the contract made it external. They should have really made it internal, perhaps, but they made it external, and therefore we can call it without passing through the pay with cashback function. And if we do that, and if we manage to trick these three modifiers and have our message.sender be some malicious contract, then we are going to be able to trick this nonce to be whatever we want it to be, because as we see here, they're casting the message.sender and they're using its consume nonce function. So our message.sender here would have to be some malicious contract. And also, yes, this is what would allow us to mint the NFT. And we can also pass in the correct amount for each currency in order to max out the cashback. So let's just get started and do some coding at this point. So I'm just going to paste everything into Remix. And I'm just going to add a contract. Cashback.sol. I'm going to paste it. I'm going to open EIP77. Let's just open 721 in OpenZeppelin GitHub, because I do believe we will need it later on. And then I will just copy this substring. I'm going back to Remix. I'm going to replace contracts with this substring. And there our contract compiles. And let's right away make an attack contract. So the first thing we need to know is that we need to get the currencies, the supported currencies that we must max out. And actually, let's just do the attack function, which will make external. And here, so the supported currencies, let's see if we can have some supported currencies. Now, in order to do that, what we can do for the sake of time is that we can actually get the level address and check it out on Sepolia Etherscan. And see what it looks like. And we see that on the create instance method, we are passing in the native currency, which we have in the contract, and we're also passing some kind of freedom free address, and the free address is public, and it's the address of some freedom coin. So we can read we can simply get the freedom coin, and we have the native currency here. So let us just initialize first of all the currency, which we'll call native currency, and it's going to be currency.wrap this address. And let us just cheat a little bit and just declare some free variable, which I think is an address, and let's make it public. And here I will compile this, and I will go into the Sepolia extension, and yes, I will deploy the attack contract, but I need my instance address. And let's actually also declare it here. Here. Because I do want the cashback instance. And this is going to be basically cashback payable of my instance address. And now let's call the free function. And this does not seem to be working. So address of free, address public free. And of course, because it's not actually the instance address, it's the level address. Because the free, yes, this free variable lives at the level address, not the instance. So we need to take the level. And that's what we need to apply. So let's just redeploy this at the right address. And here we go. We have the address of our freedom token. And we will no longer need it here. So I'm just going to paste this, and it's not going to be a native currency, but we're going to call it freedom currency. And we're going to paste the correct address here. So there we go. Furthermore, we need to basically now, we're going to be calling the function cashback dot accrue cashback. So we're going to be calling this function directly on both currencies. So we need the currency and the amount. So our first currency is going to be the native currency, and then our other currency is going to be the freedom currency. And the amount is going to be an amount that will max out each currency. And for that, we will simply copy the formula, which is here. So this should be our formula, but this has to be a max cashback. And so our amount, if we solve for amount, is going to be max cashback times basis points, which is actually 10,000, and divided by cashback rate. And this is going to be the amount. And I'll put it to the left. So let's just call it native amount is equal to native max cashback divided by native cashback rate. And it's going to be a uint 256. And in the same way, we're going to have a freedom amount, which is going to be a freedom max cashback divided by the freedom cashback rate. Here we're going to put the native amount, and here we're going to put the freedom amount. And so now we simply need to compute these quantities. Actually, yes, so UN256 native cashback rate equals, then we're going to have freedom max cashback equals, and freedom cashback rate equals, and we're going to put it UN256 in front of each. And for, to get this, we can simply use our cashback instance. And let's just look at our properties that we have. So to get the max cashback, we can just use this. And we need to pass in a currency. This would be a native currency. Let's do the same thing for the max cashback. This is going to be the freedom currency. There we go. And finally, for the cashback rate, we can use the other mapping that's called cashback rates. Again, native currency. This is going to be the freedom currency. So now we have this, this contract. And let's take a look a little bit at the modifiers that we have to bypass. So first of all, let's take a look at the only unlocked modifier that we have to bypass to call this function. And the only unlocked modifier requires our tag contract to have an isUnlocked function, which we would always like to return true. So let us do that. Function isUnlock, we'll make it public. It returns a Boolean, and we're just going to have it return true. And I guess we can make it pure as well. Furthermore, we need, so only on cashback, I believe, is okay, because only on cashback simply compares address of this to the address of the cashback account, which is going to be the case if we simply call this accrue cashback function without delegation. So we're going to pass this particular modifier naturally. And then we're only going to care about this only delegated to cashback modifier, which is a little bit complicated, but we will discuss it a little bit later. For now, let's just assume we can pass this modifier. And we basically need a malicious consume nonce function. So let's just copy this. And we also need to think a little bit about what we want to do here. Because in principle, we want to simply return 10,000, right? Because it's when we are at 10,000 that we actually mint our NFT. But here there's something that's a little bit tricky, and I need to explain it. It's that when we mint an NFT, now this, you can't really know this from the contract. You need to kind of play around and inspect and mint. But basically, when this function is called, it mints an NFT whose ID is message.sender. So it mints the NFT to the message.sender, but also the token ID will also be message.sender. And again, that is not something that's obvious, but you'll just have to take my word for it here for the sake of time. In real life, you would have to kind of test it out and inspect it. And what will happen here is that because the token ID is the message.sender, and here we're basically going to, in our attack contract, we are going to call this accrue cashback twice. And here I believe, something went wrong. I might have pasted a little bit too much. Let's just see, what the hell did I do? Yeah, so this is fine. Yeah, I think I pasted a little too much there. Yeah, pasting is not my forte, I suppose. But yeah, basically, we're going to call this twice. And because we're going to call it twice, we cannot, with the same message.sender, which is going to be the address of this attack contract, we cannot mint twice. We cannot mint with the same token ID. It's going to throw an error, and it's going to revert right here because success is going to be false. So we can only mint once in this particular thing. So we need to adjust our consume nonce to mint only once. So let's just introduce a Boolean, which we're going to call minted. Yes, of course, it's just bool. And here we're simply going to say if minted, if we have already minted, we'll just return 0. Otherwise, we're going to set minted to true, and we're going to return 10,000. And we don't need any of this. So this way, we will only mint one NFT, and the other NFT, we will get it in some other way later on in the video. So I hope that made sense. So we are minting the NFT here. We have the consume nonce function. We have the is unlocked. So at this point, after we have minted the NFTs, we need to transfer the points back to the player. So let's actually get our player address, because at this point, the points belong to the attack contract. We want the player to own those maxed out cashbacks. So let me just get my player. This is my player address. So in order to transfer points back to the player, we need to use the cashback instance. And the cashback instance is an ERC1155, if I'm not mistaken. And it does have an address, safe transfer from. So from, we're going to say address of this to the player. The token ID is going to be the native currency, but we need to transform it to an ID by using this method, which is offered to us by the library. The value has to be the max cash out, so native max cashback, and the data is not necessary. And we're going to do the same thing for the freedom coin currency. And so here our player will now have all of the points, And finally, we need to transfer the NFT. And actually, now that I'm thinking about it, we don't have the NFT address. And for that, let's see, I have an attack contract. I will need to deploy or to check out the instance. So let me just deploy a cashback at the instance address. So cashback, and we will have a super cashback NFT view function. So we'll just have it, and we'll say address NFT is equal to this. And then it is an EIP7702. So we're just going to cast this address, and we're going to call the transfer from function. And I do believe we have it here, so let's just see this function, and it looks like this. There we are. So from is going to be, again, address of this to the player. And here, again, it's going to be the token ID will be the message.sender, which was just address of this once again. But in order for this to work, because an address is actually 20 bytes and we need 32 bytes, we actually need to transfer it to uint 160. And I think I have, yeah. So this will transfer us back the NFT. And at this point, our attack contract should be ready to go. So now we need to think about the third modifier that we need to pass. So we need to think about, actually, let me just find it in Remix instead. Let us think about this modifier that our function, our, basically our accrue cashback needs to pass this only delegated to cashback modifier. So let's think what does this even mean? And I'm going to write some comments here. And basically we have this message.sender.code, which is some kind of pointer. And then we take this pointer and we add 23 to it, 23 being 0x17 in hexadecimal. And so we offset this pointer by 23, and then we load an entire 32 word. And then we require it, actually before that, we cast it into an address, which is a delegate, and then we require that it's equal to the cashback account, which is a constant address. So what does it look like? Well, first of all, it's very important to see that the code is actually a bytes memory. And because this is a dynamic type, the first 32 bytes are going to be the length. So 32 bytes are going to be the length. And then only after that, we're going to have the code content. So let me just give it some spaces. Oops. And so when we take this pointer and we added 23 bytes, the pointer initially, the code, it points here. It points in the beginning of the 32 bytes. It doesn't point at the beginning of the content. So what we have here is that we have this 23 bytes that we're offsetting by this add. And then after this 23 bytes, we will have some 9 bytes here. Let me just make sure it aligns. And then we have basically we will have some kind of 23 bytes. And it's basically these it's these 32 bytes, this 9 plus 23 here. This is what gets loaded into the delegate. However, it does get cast into an address which is only 20 bytes. And it gets cast to the least significant 20 bytes. So this 23, we can write it as 3 plus 3. Yeah, 3 plus 20 bytes, basically. And again, this has to align with the code content. And so here, we now clearly see that what we have to do is that we have to set our code content, the code content meaning the content of our smart contract. We are allowed to put some 3 bytes of something, we don't really care, but the following 20 bytes have to be the address of the cashback account or of our instance. So this is what we're going to have to do. So now let's switch to actually Foundry, and let me just make a new directory, cashback helper. I'm just going to call it cashback helper, and cashback helper. We're just going to open VS Code, and we're going to open a new terminal. And here we're going to create a subfolder Foundry, and let's just go into this Foundry, or we could have called it Forge, but it doesn't matter. And we're going to initialize a Forge, so Forge init, and we're going to Forge install OpenZeppelin. And I'm just going to copy paste right away. So here, I'm just going to do remappings. Actually, is it here? Remappings.txt. I'm going to paste this. And then I will create a new contract called cashback.sol. And I will paste everything from Remix into that. And there we go. We're going to fix this. Change workspace compiler. And now in our remappings, let's just get our contracts. And we're going to change this. And there we go. So now everything compiles. And we can actually, well, first of all, I need to save. And I need to do forge build. Yeah, so there's no errors. And now we take a look at the out folder. And we have the cashback. And we have the attack.json, which I'm just going to format. And here we're interested, this is the bytecode of the constructor, and this is the bytecode of the smart contract. So this bytecode is the one that we're talking about over here in message.sender.code. This is the code content. It's right here. And so we need to manipulate this. We need to manipulate this somehow. And basically we need to make some 3 bytes. So 1, 2, 3. And what we want is that we want to inject our instance address. And our instance address is right here. So we want to inject this into our code. There we go. And furthermore, these are generally opcodes. They're specific, but these are just kind of random characters that have to do with a public address. And what we want is that we want to consider this as data. We want this to be data and basically nothing else. And so if we look at the opcodes, if we go into the EVM codes, and if we look at the various opcodes, one of the interesting opcodes is push 32, which simply places a 32-byte full word item on the stack. And this particular opcode is 7F, and it just places the entire the entire word on the stack. And so let us just use that. So let us just use 7F. But now, because we're placing 32 bytes, we would like to just add basically 12 bytes to make it 32. So 1, 2, 3, and 1, 2, 3. So this should give us sufficient bytes. And basically, the first two, we don't really care about the first 2 bytes. So let's just make them jump destinations. And jump destinations, if I'm not mistaken, they are 5B. So we'll just do 5B, 5B. And if we did this correctly, let's just see and explore it in the playground. So let's just click on playground. Bytecode, yes. So if we run it, and so we will have this entire word on the stack. And so this bytecode works. So now if we go back here and we just consider this entire bytecode, there is a small problem, is that if I take this entire deployed bytecode and I paste it into the playground, and I just need to remove the 0x, if I run it, you will see that there's a problem. Because here, we're trying to push 2, right? We're trying to push 2 bytes, which is this 00F, and then we're jumping to that location. But now that we've changed the length of our bytecode, this location is no longer good. So we see that our jump destination is at 32, seems to be at 32. It's no longer at this F location. So we need to adjust that. And we're going to write some code. We're going to do this programmatically. So back in our VS Code, I'm going to make a new folder called Node. And I'm going to change directory into it. And I'm going to initialize a new project. And I'm going to add a VM as a dependency. And then I'm going to open it. And I'm going to create an index.js in here. And we're going to write some code. First of all, I want my deployed bytecode. And my deployed bytecode, it's actually going to be this part. So just the part that was originally there, and the one that we are added bytecode. So we have our added bytecode, and we have our deployed bytecode. And let's first of all transform the deployed bytecode into an array. So make array. So we will do for let I equal 0, I is less than deployed bytecode dot length, I plus equals 2, because we're going to jump 2 characters at a time. And yeah, we need to initialize an array. So const deployed bytecode array is equal to just an empty array. And we are going to push to it. We're going to push to it a template string. And the template string is just going to be deployed bytecode.char at I, and concatenated with just deployed bytecode char at I plus 1. So this is going to give us an array representation. Let's just see if we can just see what it looks like. So node index.js. Yeah, so now we have the array representation, and now we want to find all jump destinations. And the jump destinations, if you remember the JUMPDEST, the jump destinations have an opcode, which I actually don't remember for some reason. So let's just look it up, I guess. I'm always forgetting it. Yeah, it's 5B. So 5B is the jump destination opcode. And we actually want the index. We want the index in this array whenever we have a jump destination. So let's just say const jump destinations is equal to just an array. And then we're going to do for let I equal 0, I is less than deployed bytecode array dot length, I plus plus. If deployed bytecode array at I, if this is equal to 5B, then we will just do jump destinations dot push I. Okay. And now we want to find all push to where the following 2 bytes match a jump destination. If found, we adjust the following 2 bytes. So basically, going back here, so if we encounter this push 2, which with this value matching a jump destination, we need to adjust this push 2. So instead of being 00F, we need to be, for example, 32. So let's just do something very similar to this. I'm just going to copy paste this. And now we are looking for, so the push to opcode is 61. And so we're going to try and find found destination. And we're going to do jump destinations dot find destination. And so now this destination is just an integer. So we need to convert it to hexadecimal. So we're going to use VMs to hex. We need to slice off the 0x by doing slice 2. And let's just declare it to be a candidate. And now in order to match our characters, we need to left pad it with zeros. So we'll just do while candidate.length is less than 4. We're just going to do candidate equals 0 plus candidate. And then we're going to return candidate equals the template string. And what we want is deployed bytecode at I+1, and then deployed bytecode at I+2. And here, if we found a destination, so if this is not undefined, we need to adjust it. So first of all, we need to calculate the adjusted destination. So we'll just do, well, first of all, found destination, we need to add the added bytecode dot length. But we need to divide this length by 2 because, again, this is going to be in characters and we need it in bytes, so we need to divide it by 2. And then this value, we need to transform it to hexadecimal. We need to slice off the 0x. And let's assign it adjusted destination. Oops. And we'll do the same trick as we did here, where we want to left pad it with zeros. So we'll just do this, and therefore it will be padded. And now we need to adjust the deployed bytecode. So deployed bytecode at I+1 is going to be this adjusted destination, the first 2 characters of it. And actually, let's just do 0. So from 0 to 2. So start, end, just so that it's very clear. And then I+2 is going to be from 2 to 4. And we can also adjust I to add 2, simply because we want to advance. We don't really need to check the further I+1 and I+2, since we know that we've just adjusted them, so we can just advance. Yeah, so this should give us an adjusted deployed bytecode array. And so let's just actually transform it into a string by doing join. And let us also add the added bytecode to it in front. And I do believe, yeah, this cannot be correct. Obviously, this is not the correct constant. So what is actually our added? Yeah, so it would have to be this. This is the added bytecode. This is the correct constant. So added bytecode, and we just put it in front, and we log everything. So let's see if that works. So this gives us some kind of bytecode, and let's take a quick look at it in our playground. So if I just paste it and I run it, so you see now our push 2 is 32, and we have a JUMPDEST at 32. And let's just check one more. So here we have a push 2 to 62. Do we have a JUMPDEST at 62? And indeed we do. So our code appears to have worked. So now we would like to basically send a transaction with that. So I'm just going to do a clear. And I am going to, let's just see, inside of, yeah, I guess we can do it inside of Node. I'm just going to add a .env file where I will add a private key, where you would have to set your private key. But I would also want to do my bytecode. And the bytecode, yeah, I actually sort of needed it. So let me just get the bytecode. here. And I do think I need to prefix it with a 0x. And I would also need a Sepolia URL. So this, you can get it on I believe I'm using Alchemy. So if you go on Alchemy, it's free. You can create an account and get a free Sepolia URL. And yeah, so let me just correct this. So once that's done, you can continue. And actually, we do need to make an adjustment because this actually, this right now is the bytecode of our deployed contract. But we, as a matter of fact, also need the constructor. So if I just go here and I start selecting this, I see, if you see over here, basically this is where our original deployed contract was. So I just need from here and backwards, and this would be the constructor that I need. So if I go back to my env, I'm just going to paste that in front. So we need the bytecode to include the constructor as well. And so now we can run the following command with our Sepolia URL, with our private key, and with our bytecode. However, actually, before we do that, let me just copy this command. We would like to do a source.env, and now we can run this command. Very good. And now that we have run this command, we can actually send another command, which is going to be our first attack. So we're going to cast send, but here we will cast send to our instance. So our instance is going to be this instance address. And we're also going to call well, actually, no, it's not our instance address, of course. It's going to be our attack contract that we have just deployed over here. And we're going to be calling the attack function. Yeah, so at this point, we have run our initial attack, and we, in principle, have gotten our NFTs, our first NFT. So in order to finish our attack, we're going to build another attack contract, which is going to exploit the storage sharing that is basically inherent to the EIP7702. So I'm going to create actually a contract attack2. And in here, I am going to also use a layout and I want to have a nonce. So basically I want to delegate the cashback, or I want my EOA to delegate to cashback, but I want to set, before I do that, I want to set a fake nonce in the storage of my EOA, which will then be used by the cashback. And that's going to be basically the hack. So I'm also going to have this, and I'm going to have a function set nonce. Let's just do it public. And we're just going to set nonce equals to 999. So this is just so that we can call the pay with cashback on our cashback contract just once, and it will increment us and it will grant us an NFT almost for free. And the only thing is that we might want to adjust this number. So this number, actually, let's go back to our Visual Studio Code, and let's go back to, I called it Foundry. So basically, we're going to call forge inspect, and we want to inspect the storage layout of our cashback contract. And so if we do this, we're going to see that, first of all, we're seeing this number appear. And let's just try to convert it to hexadecimal. And we see it's this 442A BA00. And so this is exactly this number. And furthermore, we are seeing that our variable of interest, which is nonce, is actually, so this would be 0, this would be 1, 2, and 3. So we need to adjust the slot by 3 in our attack contract. So we need to add a 3 here. And so this will be our attack 2 contract. So let me just go ahead and deploy it on the Sepolia mainnet. So attack 2, deploy and verify. So now that we have our attack 2 contract, we're going to delegate to this contract. And so we're going to do cast send. So basically what we want to do is that we want to use this --auth option to delegate to our second attack contract. So here we go, that is good. Let me just make this bigger. And now what we want to do is that we want to cast, basically, we want to send and let me just take here. So now we want to send something directly to our player address. So our player is right here. So we want to send this. And now we basically want, now that our EOA has delegated to our attack 2 contract, we want to call this setNonce function. And this will set the nonce to, basically, it will set the nonce in the storage of our EOA to 9,999. So that's good. And finally, we can basically delegate. So here we delegated to our attack 2 contract, but let's actually go ahead and delegate to our instance instead. And so our instance is here. So now we delegate to this instance. And now we're going to cast send, and so what are, and so let's just go ahead and look at what is the function that we're trying to call. So we're trying to call this pay with cashback function. So let me just paste it into the quotes. And let me just remove. So this is not going to be a currency, but it's actually going to be just an address. And this is also going to be an address, the receiver. And finally, it's going to be an amount. And so the address of the currency, we're going to use the native currency. So let's see. We can get the native currency from here. So this is going to be our first argument. And our second argument is going to be our player address. So we can just copy, paste it here. We're going to send it to ourselves, so to speak. And finally, the amount can just be 1. And so this should grant us another NFT because, as I said before, we have just previously set our nonce to 9,999 using set nonce here in our second attack contract. So let's just see if that works. And it appears to have worked. If something didn't work, we would have almost certainly had a revert. So if I just go back and try to submit the instance, and there you go. So this was a very challenging, basically, Ethernaut. So I hope you enjoyed. I hope you learned a lot. I certainly did. Oh, and actually, before I forget, it's always good practice to reset our account to what it previously was. So we're just going to send, we're just going to redelegate to basically nothing so that our account isn't actually associated to any smart contract. So that way it will avoid any future problems that you may have.